How's it going, everyone? Welcome. Eliar Gonzalez again. Exploring now the RxJS, which is part of these abstractions that we need when we are developing JavaScript applications. So, because if you are a UI specialist or a backend developer that write your web apps for companies using this language, you might want to know down deep how these particular abstractions, or aka these tools, this approach to solve common problems that happen in our code base as we develop all of these web apps. So here, because this is exclusively for asynchronicity, which means is that when you write your UI, you don't only specify or you don't only focus on the UI details, such as is like, hey, how this element is gonna look like, is this input is close enough, or is this button actually matching the Figma designs or any sketch design, you so on and so forth. The idea is to also deal with the communicational aspect, particularly the concurrency, tasks that overlaps at a time. And now, because in JavaScript, this particular language that is a single thread means that it evaluates one statement at a time, and a thread and a process. Is important to understand this because now a thread is one of the components of a process, and a process is what happens when a program, an executable file, is mounted to main memory that live on disk, and then is executed by the CPU. That makes a process. So this process are, and this is quite important to recap because here from this byte go here, especially on the threads, shout out to byte go, absolutely. He mentioned that this is now a fan interview, but I think this is not a fan, man. It's like, this is if you really wants to understand how the things work, because at the end of the day, if you understand how this machine works, it will be much more easy to go with, especially to solve some of the problems, not only for your daily life, but also for your clients. So explaining this difference between the process and the threads is something that I'm going to explore right now. So then we can move on to what is relevant in today's video, that is RxJS. All right. So how can we now deal with this series of eventual values? And we're gonna see that. Bear with me. Okay. Yes. Fair use.
What's the difference between process and thread?
This is the fundamental here. So far we have described that now a process is when a binary executable or a program that live on this is mounted on memory, and then then it is executed by the CPU. This made a process.
This is a common interview question. Let's take a look. To better answer this question, let's first understand what a program is. A program is an executable file. It contains the code or a set of processing instructions that is stored as a file on disk. When the code in the program is loaded into memory and executed by the processor,
exactly. So when the program is loaded into memory and executed by the processes or by the processor, it becomes a process.
An active process also includes the resources the program needs to run.
An active process includes resource that this process needs to, that is managed by the operating systems. So it means that is, hey, it needs rent, It needs perhaps access to the input and output. It needs CPU.
These resources are managed by the operating system. Some examples are processor,
And then we look at some example of processes.
registers,
So
program
process
counters,
register,
stack
process
pointers,
counter,
memory pages
stack
assigned to the
pointers,
process
memory
first heap and
page.
stack, etc.
So you have now process register, program counters, and a stack pointer. This is a couple example of processes. So with the stack pointers, you say, hey, at which point I am in the current program, or the program counters is now count is which is the line of code that it is. Processor registers is that's okay. Let's dive deep into this. Okay. What is a process register, counters, and stack pointers? Exactly. Stack pointers, a memory page. In a process. So, program counter track the next instruction to execute. Status register contains flags indicating process states and conditions. And general purpose register is whole data being actively processed. Counters in process context typically refers to instruction counters, time slide counters, and event counters. Track specific events like input and output. And the stack pointer is a special register that points to the top of the process stack, manage function calls, local variables, and return address, move up and down on items, and push pop from the stack. A memory page are fixed size of block of virtual memory, typically 4 kilobytes or larger, allowing efficient memory management and sharing. Enable virtual to physical address translation. Can be individually mapped, protect, or swap to disk. From the basis from memory isolation between processes. Make a couple example of each individual process in C++, right? Yeah. Again, you have to be careful with all of this. All of this code that was generated, but as you can see, it access to the input and output, the vector and the thread. So the code demonstrates register with program counter, for example, like this: register simulation, process counter, instruction count, time slides in its operation. It also have the executable operations and perform input and output. But the point of this, right, is to at least understand now what are the most common example of processes. So you have program counter that tracks the next instruction to execute, the stack, okay? So program counters, it tracks the next instructions to be executed, the process register, the place or how it's going to hold memory, okay? Whole data being actively processed, and the stack pointer, which is points to the top of the process and manage function calls. For example, stack pointers is manage function calls. So it manages function calls, local variables, and return address. Interesting. But again, this is couple of this example, as well as memory page. This is for this is a process for efficiently manage is the memory. Fixed size block of virtual memory. Interesting. So behind the scene, it's actually doing all of this kind of stuff. And I'm doing this is just to recap about that. So let's go is to actually write this parallelism and the kind of stuff. Understand now the sort of difference between process and threads. So process is an independent program with its own memory and resource, right? In the process, so let me actually put it here. So a process, and okay, when an executable, you can say something like what French toast. Okay, so this is a process. So when an executable file that contains, okay, so when an executable file that contains is instructions that contain a set of instructions, when an executable file that contains a set of instructions typically store on disk, okay, and yep. So when an executable file that contains a set of instructions that is stored on disk and is loaded into memory and executed by the processor, it becomes a process, right? And executed by a processor, a set of instruction that is stored on disk and is loaded into memory and executable by process, it becomes a process, right? So this is common examples. Exactly. So an active process include resource like CPU, memory, or input and outputs that are managed by the OS. All right. So, okay, that are managed by the OS. So, all right. So common examples of process are program counter, no, program register, which holds the data for the active process. Program counter indicate the next line of the code. Okay, track the next instruction to be executed. So tracks the next instruction to be executed. That's right. So program register, program counter, stack, okay, manage function calls. So manage function calls, right? So manage function calls, local variables and return address. Manage function calls, local variables, and return it address. And now the memory page, which is for efficiently store, efficient memory management and sharing. Efficient memory management. Okay, efficient memory management and sharing by fixing the length, or by fixing size block of memory, by fixing size blocks of memory. Pretty much like you when you, let's say, your fridge, all right, that you now have everything organized into their own particular space. So here is vegetables, cheese, butters, and then you have now meat or fish, or perhaps you are vegetarian and then you like to store in your fridge some other stuff. But the point of this is now the memory page, this program that has now this fixed length virtual memory for memory efficient, for memory management, for an efficient memory management and sharing. But this is quite interesting because all of this kind of stuff is just now things that this kind of language actually doing for us, right? So here we're going to explain now an interesting property.
One process, each process has its own memory. Important property of a process.
Which is properties. Like that. So an important property on the process is that you can, right, let's see here, there, process, an example, okay, examples, properties, like so. So an important property of the process is that it have one single store in memory.
That is worth mentioning. Each
So an important property of the process is that each process have their own memory address, or their own memory space, or memory address space.
Process has its own memory address space. One process cannot corrupt the memory space of another process.
So one process cannot corrupt the memory space of another process.
This means that when one process malfunctions, other processes keep running.
Which mean if a malfunction process happen, other processes keep running.
Chrome is famous for taking advantage of this process isolation by running each tab in its own process.
So Chrome is famous for this by isolating each tab into a process, right? So if one misbehave, misbehave, it won't impact the others. And this is quite interesting to understand that.
Execution within the product. Now, what is a thread?
And then you have now the process that is like that. Okay, so it can communicate. It can communicate with others through IPC, inter-process communication. Such as, exactly. So it can communicate with other processes, space in memory, because each one of them has their own memory address space. So each processes can communicate through the inter-process communication, whether it's a pipe, which is unidirectional, or multidirectional using sockets, or by sharing memory like a dashboard, all right, or message queue. So they have some sort of broker for that, like a post service, or sending signals to one program. This is very interesting. And now let's going to talk about is a thread, bro. A thread, bro. So a thread is a small unit of execution in a process, known as a worker. Okay. This definition comes from here, but let's actually take exploration here.
A thread is the unit of execution within a process.
Exactly. Define a unit of execution within a process, shall we?
A process has at least one thread. It is called the main thread.
So a thread is a small unit of execution in a process, right? A process or a thread or a process can contain a process has at least, right, a process has at least one thread called the main thread. So it has at least one single unit of execution.
It is not
Interesting. It has one single unit of execution. So it is not uncommon for a thread for a process to have several threads.
common for a process to have many threads. Each thread has its own stack. Earlier we mentioned registers, program counters, and stack pointers as being part of a process. It is more accurate to say that those things belong to a thread.
So it's not uncommon for a process to have several threads. Each process or each thread, each unit of execution, each thread, all right, so each unit of execution has its own program counter. It makes a lot of sense. Program counters to say, hey, what is the next line or what is the next instruction to be executed? A program counter, a stack. Hey, I'm going to manage the call stack variables, local variables and return address, and the program counter, stack register and program counter stack and registers. How am I going to hold this data? So this unit of execution that has its own program counter which is the next line of the code I'm going to execute. In the stack, hey, I'm going to manage the call stacks. I'm gonna manage the call stack, local variables, and return address, and the registers. I'm going to manage this. How am I going to hold the data for these active processes, or for this active unit of execution in a process?
Stack. Earlier we mentioned registers, program counters, and stack pointers as
So for example, with JavaScript and C++, but in your case with JavaScript, we have now this particularly implementation of a threads of this unit of execution that is made of the call stack. Hey, I'm going to now keep track of which line of the code I'm currently at, as well as function calls, and you have now the global execution context, the global and the function execution context that is created to evaluating is one line at a time, which is a single thread. It has only one single unit of execution, right? Where you have now your local memory and your thread, all right? And also have the heap, which is the program register. How am I going to handle this memory? A place where you can dump memory for this app, a place where you can dump data on this memory while this active process. And then you have now other aspect of the language, which is part of the threads, but it's very specific to JavaScript, and that is the event loop, the coordinations between now different call stacks or different queue. The micro task, which is for promises, for handling is now the asynchronicity or programs, at least for one single eventual value, and the callbacks to handle is the timers, because now this is not native to the language. That's why we also have is the web APIs or the server API. It makes a lot of sense. Oh, here we go. Oh my God, you need to do this, man. Hola. 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 Hola, sí. Ah, voy bajando, amigo. Hold on. I bought a couple peanuts and some sort of seeds. So bear with me. Hold on. All right, and we are back. So that's right. This is thread, right? So a thread is a small unit of execution in a thread where a process has has at least one thread called the main thread, and it is not uncommon for a process to have multiple threads. So each thread has its own stack which manages the function calls, local variables, and memory return address, program counters to indicate, hey, what is the next line, or keep track the next line to be executed, the register to hold to manage the data that's gonna be whole, and it means that this is our part of this single execution, or this single unit of execution. So JavaScript has its own implementation of a thread that is made of the call stack, the global execution and function execution, as well as the stack or the heap in this case, and also some other stuff that it needs due to the single thread nature, which is the event loop. This coordination between different queues. So for example, the callback queue, which is now how you can access to the timers, how you can defer tasks that will take some time to complete. This is not native to the language. This is now provided by the platform that JavaScript is running, which is the web, or right now it can be on the server. Thanks to the Ryan Dahl hard work and all the Node.js community around it. So the point of this is it also has the micro tasks, which is to handle this now future values that will be completed at some point in the future. That has more priority than the callback queue. But once you understand this single unit of executions, which is also known as a worker, you can now dive deep into this concept and understand what is doing behind the scenes JavaScript. So, because this is a thread, and I get it why this is a common concept between the process and the threads.
Being part of a process.
Because you need to be very, you need to have that like a second nature. You know, it's like that should be like breathing for you.
To say that those things belong to a thread. Threads within a process share a memory address space.
Mm-hmm.
To a thread. Threads within a process share a memory address space.
And a thread has a shared memory.
To a thread. Threads within a process share a memory address space.
Mm-hmm. Threads between a process share a memory address space, because at the end of the day, process has its own memory address space. Similar like you put things on the fridge, all right? They have its own particular space. Hey, this is for vegetables, butters, and cheese, bread, if you like to buy some bread, and this is beer and all that kind of stuff. And perhaps you would like to buy some meat, right? If you are carnivorous, or pescatarian, you want to go with fish and all that kind of stuff. But that's quite interesting. So a threat between a process, a threat, or this is threats in plural, right? So threats between a process share the memory address space.
It is possible to communicate between threads using that shared memory space.
Mm-hmm. Making them or making the communication across them possible. Possible through the heap.
However, one misbehaving thread.
Mm-hmm. However, one misbehaving thread can bring down the entire process.
To bring down the entire process. How does the operating system run a thread or process?
Okay, and I would say, how does the operating system run a thread or a process? Exactly, run a thread or a process. And I think starting from this is something that will clarify a lot of ideas. So how does an OS run a thread or a process on a CPU? Okay.
Yes, on the CPU. This is handled by context switching. Operating system run the thread or process on the CPU.
Mm-hmm. Exactly. How does an OS run a thread or a process in a CPU? This is done by context switching.
This is handled by context switching.
This is handled by context switching.
During a context switch, one process is switched out of the CPU so another process can run.
This is handled by context switching. This is handled by context switching. So, okay, so the way of how now a CPU, or particularly how the OS run a thread, this single unit of execution or a process, okay, or all of this set of instructions, right? Mm-hmm.
Context switch, CPU access. How does the operating system run a thread or process on the CPU?
Mm-hmm. Exactly. How does the OS run a process or a thread on the CPU? This is handled by context switching. This mechanism, this concept.
This is handled by context switching. During a context switch, one process is switched out of the CPU.
So during a context switch, one process is
switching. During a context switch, one process is switched out of the CPU so another process can run.
During a context switch, one process is out. Switching out.
One process is switched out of.
Exactly. One process is switched out
of the CPU.
God damn, that's wild, bro. That's wild. It's like you're trying to do one task and then you swap to an, and then you receive a task from another stuff that might be related or not. Uh, Holy moly, context switching.
So during a context switch, one process is switched out of the CPU so another process can run.
During a context switch, one process is switched out of the CPUs so another process can run.
The operating system stores the states of the current running process.
The operating system store the state. Okay. The operating system store the state of the process.
So the process can be restored.
So the OS store. Interesting. So the OS store the state of the program.
System stores the states of the current running process, so the process can be restored and resume execution.
State of the program.
States of the current running process, so the process can be restored and.
So the OS store the current state of the processes, so they can resume
execution at a later point.
So they can resume execution at a later point. Okay, but this is what's going on behind the scenes. Is this context switch? Jesus. This is okay. So this is now the way how the OS runs a process or a thread on the CPU, and it has this schedule, and this is done by the context switching. So one process, so the OS. Okay, so one process is switched out of the CPU so another process can run. Jesus, this context switching. So okay, so this is what's going on, especially when you are now running one program and then another one and then another one, or aka by process. Okay, for example, this and here and here and here. So behind the scenes now is the OS that is handling is this context, is handling is the way how the process and threads run on the CPU. So it now passing that through the context switching, which is a mechanism that it has. So it switch out the process. So it switch out of the CPU one process so another process can run, and you do that anytime you want to actually is run a particular process. And because browsers are famously known, Chrome is famously known that each independent tab has its own process. So that's exactly what it's doing behind it. It's context switching, it's context switching, it's context switching, it's context switching, it's context switching. So the OS now store the current state of the process so they can resume. So for example, let's say we go to bye go, right? Say, hey, it's gonna click here. This is not a new state of this process, and if you now navigate back to this another process, it do this context switching. Mm-hmm. And this context switching, which is handled by this mechanism, and now the OS is to store the current state of that process, so you can resume the execution at the later point. This is how now things are starting to work behind the scenes. That's huge. That's massive. What is the trade-off of this? Because there is a trade-off of this.
It then restores the previously saved states of a different process and resumes execution for that process.
Mm-hmm. So the OS store the current state of the process so they can resume at a later point
The previously saved state and resume execution at a later point. It then restores the previously saved states of a different process.
It then store the previously state. Okay. It then store the previously state of another process and pass it to the CPU.
And resumes execution for that process.
Okay, so the OS store the current state of the process so they can resume at a later point. It then store the previous state of another process so they can resume. So they can resume at a later point.
Different process and resumes execution.
So they can resume execution.
Then restores the previously saved states of a different process.
So the OS store the current state of the process so they can resume execution at a later point. It then store the previous state of another process or a different process. It then store the previous state of a different process so it can resume at the previous, so they can resume
and resumes execution for that process.
in a different process and resume execution from that process. But this is part of the context switching. It's a hey, this is one process is switched out of the CPU so another process can run. So the OS hold the state of the process so they can resume the execution at a later point, and then a previously stored different process can resume execution from that.
Context switching is expensive. It involves saving and loading of registers.
So context switching is expensive. Context switching. Context switching. So context switching is expensive. It involves store the state of the process. Yeah.
Context switching is
It is-
expensive. It involves saving and loading of registers.
It involves saving and loading the state of a process.
Switching out memory pages.
So context switching is expensive. It involves saving and loading the state of a process.
Expensive. It involves saving and loading of registers, switching out memory pages, and
Switching on memory pages. Switching on memory pages.
updating various kernel data structures. Switching out memory pages and updating various kernel data structure.
Context switching is expensive. It involves exactly saving and loading the state of a process. This is a trade-off. Context switching is expensive because it involves saving and loading the state of the process, switching on memory pages, and modifying its data structure.
Switching out memory pages and updating various kernel data structure.
Jesus, and updating various kernel data structures because you want to keep track of those state change, and updating various kernel data structures, kernel process state. Kernel process table, per process region table, kernel region table, and main memory.
Switching execution between threads also requires context switching. This
Switching execution between threads also requires okay. Switching execution across threads requires also context switching.
switching execution between threads also requires
Switching execution between threads. Between threads requires also context switching.
It is generally faster to switch context between threads than between processes. There are fewer steps to switch context between threads
Save context and restore context
than between processes. It is generally
and over time.
faster to switch context between threads than between processes. There are fewer states to track and
It is usually it is less expensive. It is less expensive to switch threads than processes. It has less state to keep track.
More importantly, since threads share the same memory address space, there's no need to switch out virtual memory pages.
And it has less state to keep track. And more importantly, since they have the same, oh man, my God, I get it. And more importantly, since they have the same memory space, it doesn't involve
The same memory address space. There's no need to switch out virtual memory pages.
There is no need there is no need to switch between memory pages. Memory pages.
which is one of the more expensive operations during a context switch.
Which is one of the most expensive operations during a context switch. The memory pages.
Virtual memory page share the same memory address space. There's no need to switch out virtual memory pages.
There's no need to switch between virtual memory pages, which means that you don't need to actually encapsulate or to split or to segmentate that space.
Which is one of the more expensive operations during a context switch. Context switching is so costly. There are other mechanisms to try to minimize it. Some examples are fibers and
It's doing this virtual memory page, so you don't need to virtualize memory page. Context switching is so expensive that there are other mechanisms here.
There are other mechanisms to try to minimize it.
There are other mechanisms to minimize this.
Some examples are fibers and coroutines. These mechanisms trace complexity for even lower context switching cost. In general, they are cooperatively scheduled. That is,
they are cooperatively scheduled. This is known as cooperative concurrency or cooperative multitasking, also known as non-preemptive multitasking. It's a style of computer multitasking in which the operating system never initiates a context switch from a running process to another process. Instead, in order to run multiple applications concurrently, processes voluntarily yield control periodically or when idle or logically blocked. This type of multitasking is called cooperative because all programs must cooperate for the scheduling scheme to work. In this scheme, the process scheduler of an operating system is known as the cooperative scheduler. The process scheduler of an operating system is known as cooperative scheduler, whose role is limited to starting the processes and letting them return control back to it voluntarily. This is related to the asynchronous programming approach, which is exactly what we are here. Asynchronous programming approach.
You control for others to run. In other words, the application itself handles task scheduling. It is the responsibility of the application to make sure a long-running task is broken up by yielding periodically. This concludes our discussion of process. Other mechanisms to try to minimize it. Some examples are fibers and coroutines.
Fibers and coroutines. Fibers and coroutines.
These mechanisms minimize it. Some examples are fibers and coroutines.
fibers in code routine.
These mechanisms trace complexity for even lower context switching cost.
So this mechanism trade complexity for even low cost or lower context switching, lower context switching cost.
In general, they are cooperatively scheduled. That is,
in general, they are cooperatively Jesus. In general, they are cooperatively in general, they are cooperatively cooperatively
same as cost. In general, they are cooperatively scheduled.
Okay, they are cooperatively scheduled. It's a hey, one you, one I, one you, one I, one you, one I.
That is, they must yield control for others to run. In other cooperatively scheduled. That is, they must yield control for others to run. In other words, the lower context switching cost. In general, they are cooperatively scheduled. That is, they must yield control for others to run.
They must yield controls for others to run. They must yield control to others to run. They must yield control for others to run. They must yield control for others to run. It's like, hey, I yield control. Similar to the generator, because at the end of the day, that's what a generator is doing. It's like, hey, I'm yield control. I pass control to whoever called me. They must yield controls for others to run.
In other words, the application itself handles task scheduling.
So, in other words, the application itself handles task scheduling. In other words, the application itself handles the task. The application itself handles the task scheduling.
It is the responsibility of the application to make sure a long-running task is broken up by yielding periodically.
But it's not the application level. In other words, the application itself handles the task scheduling, and it is the responsibility of the task of the application to yield the task periodically. To make sure long-running task is broken up in yield, and it is the responsibility of the application to make sure long-running task is broken up by yielding periodically. Is broken up and yielded is broken up by yielding the task periodically. So a good example of this is that here, let's get into this. What? For example, like this. So periodically, so in other words, the application itself handles the task scheduling. So the responsibility of the application to make sure that the long-running tasks are broken by so these learning tasks are broken up by yielding the task periodically. So for example, a task like hey, I want to now is create a Fibonacci sequence. So let's say here you create a function, in this case a functor or a generator. You say hey, is to Fibo. It's a Fibonacci, and here you say hey, I want to now is have this tuple here, which is the current and the next value. Okay, that will be in a tuple of 0 and 1. Okay, and then while this is true, which is something that I'm gonna do indefinitely, okay, this long-running task, it say hey, I would like to schedule this task periodically. So it is now the responsibility of the application to make sure that this long-running task that we're about to do, for example, in this case generating Fibonacci sequence or polling, doing so HTTP polling, are broken up and yielding the task periodically. Broken up means that let me actually is now like this and say hey, the current and the next. All right, the first iteration here, I want to now do something like this. All right, let me actually is saying yield the current. All right, and after that you get into this execution. You say hey, I want to now is update those values here by saying hey, now the current and the next will be is now whatever you have now on the next in the current plus next, right? So hey, I want you to now update this and then assign this value to that. So to make sure that we didn't lose our mind, okay?
We're done here.
Like that. Or you can say is well, something like this. You can actually get that and say now this will be the values. Okay, you may want to actually you may actually want to create now this and say hey, this will be now the values for that, which is doing something like this. Okay, and you say, hey, get me is those values, which is the current, the next, from the values, right? From the values, yield that, right? And well, actually now update those values after that iteration, which is now saying, hey, so values will be now is whatever you have the next and the current plus next. Right, so if you do this, of course, you're going to run into a infinite sequence of values. Another good approach maybe is, hey, I want you to now receive some sort of, I want to now is get the number of iterations that are going to do, right? So it is now at the application level it is now the application level here. Let me go back to this. Asynchronicity here. Don't wait for the main thread's call stack. Semaphores. Recurrency. There you got it. So in other words, the application itself handles the task scheduling. So here we are now looking at an example of context switching that is so expensive that now there are several other mechanisms for doing that, like fibers and code routines. In general, they are cooperatively scheduled. They must yield controls for others to run. Ellos tienen que dejar pasar el control para que otros puedan ejecutarse. Cooperative concurrency. So in this case, so if we use, for example, now here, say, hey, these iterations, I want you to go and do this as long as the number of iterations are less than this iteration, for example, like this, all right? And our iterations start with 0, right? Let me assign this variable so you can, so here we are declaring and reassigning that. And you got it, so iteration. And at the end of the day, we're going to now update the iteration, because otherwise it will do this forever. Right, so when we call this Fibonacci here, all right, where we create initially our iterator, right? And if we want to actually use the for loops way to consume iterators, which is for, they say, hey, let or count of the values here of the iterator. That we have a reference here. So please now, well, give me is the values as expected, right? Say redeclaration of the var it. Wait, what? Redeclaration of the var it. Okay. Preload this. Okay, redeclaration of the variable it. Oh, and it's because we need to pass is the iterator dot next. Is iterator dot next? But it say is redeclaration of var it. Jesus, I get it. Yep. But because we already have this iterator, as long as you follow is the iterator protocol, you must actually iterate through all of this. And it say that it's var. Okay. Perhaps this is for this particular tab. Yep, might be this tab. Because if I run this into a different tab, okay. Okay. It's because the condition here, as long as the iteration is less than the iterations, because we didn't pass anything here, we can say, hey, initially it will be is 10. If we don't pass anything here, and we can pass this a number here to do that kind of stuff. But as you can see, it does this at once, synchronous. Add once and synchronous. Just like that. Right? So, the idea of this is that we now, from the application level, have to coordinate, have to schedule all of these long running tasks and break down by yielding them periodically. We are here yielding that periodically. We can also say, hey, now let's go and say something like this, which is yield this value, which is now called a set timeout. Okay. But this set timeout right now, what is going to be handled is something like this. This coordination stuff becomes this quite lengthy and verbose. You say, hey, timer or interval, let's going to call this interval. This will be now a function, simple function that is going to run until completion. And here interval will say, hey, let's go to now the initial interval, which is the time. Initially will be 100, 1000, right? And we say, hey, let's go to now call this underlying API that is not native to JavaScript. It is provided us by the web platform, and then we say, okay, we want to actually is after that console.log the value, which is whatever you have now on that iterator dot next, right? Dot value. So we want to access to that and then show the proper value after, well, an X amount of time for this. So now we are not going to consume that here, okay? And in fact, it'll be here where we are going to do this kind of stuff. So by the time we call now the iterator here with the Fibonacci, for declaration of let, okay, that's right. Yeah, that's right. We need to actually consume that. We will need to consume that. Okay, no problem. Oh, I get it. I get it. Is yielding that interval. So it means that it's calling this function, and this function here now is going to, it's yielding this, which means that it's pass control to this. It's now calling this. Okay, but you need is to pass this the value there. Yep, you need to pass is the value here. That's what happened. So you need to pass is the French toast. So you need to pass here is the value to this, which is the current. So once you receive that current value, let's put this here, just like that. And once you receive that value here, now you're going to do is now console.log that value, okay, and now call that function here. So go to the next iterator, to the next, to the next, to the next, and so on and so forth. So now you want to use the IT, the generator, that's right. So let's go to now consume those values, which is by saying, hey, this one. And of course it throws me all of that immediately, and then all of this. So we reset this. Exactly, it does this after 1 second as it is. So, but the point of this iteration is that you are now passing control to someone else. In this case, at the application level, you need to schedule this long running test by periodically yielding those values, so breaking down and periodically yielding those values. But this is the idea behind this, all right, of about processes and threads, and how it's important not only for all of this code interview and that kind of stuff. No. It's for you to understand deeply how the JavaScript thread concept means, which is come from the general aspect, and then now narrow down your focus on the JavaScript, so you can have much more so you have now a more practical approach of all of this. So that'll be all for this video. Take care. Bye bye.